All right, AP Chem kids. So it's Saturday at it's about 1:25, and I'm kind of doing this as a preemptive thing for Monday. So this is when I'll send this out because it's just supposed to be miserable on Monday, and we're not going to have school. And so this way, I've already got the video done. So let's chit chat about some questions on this that I gave out on Friday, which is going to be due today, right? Monday. So, so this is talking about protons, neutrons, and electrons in a magnetic or electrical field. So, to generate an electrical field is pretty simple. If you just take like a balloon, right, and you give it a rub with your hair, okay, right? So that's generating an electric field, okay? Just messed up my hair, okay? So it's pretty simple to do. You can have a battery, things like that. So electric fields obviously only affect neutral particles. So, excuse me, charged particles. Neutral particles like neutrons just pass right through. So that's kind of the hint on number one. Now, on question number two, you're talking about Rutherford. Remember, Rutherford did the gold foil experiment. Okay, he had a sheet of gold foil. He shot alpha particles. Now, the reason he called them alpha particles was because he didn't know what they were at the time. And everybody has this vision, like you could actually see these particles. You can't see them. They are a helium nucleus, and the alpha particles are He4 2+. That's an alpha particle. So basically, he shot these particles in, and he would look, and he had a phosphorescent screen around the back of it. And whenever these particles would hit, you would see a flash of light. So you couldn't actually see the particles, you would just see the lights that they were emitted. And most of the time, these particles went straight through. Every once in a while, one would hit, and it would get deflected. About 1 in a million, one would hit, and it would bounce back. So out of that, Rutherford had to conclude that even though this looked like a solid, when he shot these alpha particles at him, most of them went straight through. But because he knew that they were positively charged, therefore, the only way it could bounce back is if it hit something else that was also positively charged. So that's how he concluded that the nucleus was very, very dense, was very, 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 very small, and it had a positive charge, because that's the only way he could hit and make that thing bounce back. So it was 99% empty space, everyone would hit and it would bounce back. So keep that in mind when you answer number two. All right, so when you get to number three, you're talking about mass number, atomic number. If you're a little fuzzy on that, Google it, look in your book. Mass number, total number of protons and neutrons. Atomic number is the number of protons. When you get to something like number 6, where you've got the average atomic mass of neon is 90%, it has a mass of 19.992, 10%. So think about it, this is like a quiz. 90% of the people in the class got a score of 20 on the quiz. 10% of the people got a score of 22. Okay? Well, you're going to try and find the average. Well, clearly, your average is going to be closer to 20 than it is to 22, because that's the score that 90% of the people got. And you're going to use this later on. So you're going to take 0.9 times 19.992 plus 0.1 times 21.991. Add those together, boom, there you go. Or you can take this times that, take 10 times that, add them together, and then divide by 100. It doesn't make any difference. But here's what I want you to see. Your answer has to be somewhere between 20 and 22, and it's probably going to be closer to 20 because that's where 90% of the isotopes have that mass. So just keep that in mind. On number 8, when you're talking about that mass spectrometer, remember, kind of like my hair, okay? So imagine this is like a mass spectrometer. And so my hair, these hairs, right, stick up. I'm guessing they can. I can kind of hear them. My hairs stick up because of the fact that they're going to be deflected a lot because of the fact that they don't have much mass. Now, I'm not going to put this on my arm and then all of a sudden my arm's going to go like this because my arm has a lot of mass. But so, number one, and this goes back to that first thing we talked about, electric fields only interact with charged particles. When you get to number 10, okay, the mass of an AMU, remember that stands for atomic mass unit. So if you were to take like a proton, and what's defined as one atomic mass unit, which is about a proton, that's equivalent to 1.66054 times 10 to the negative 24th kilograms. Now, for those of you that are in AP Physics, you'll eventually see how we actually got that number, which is tough to do. Look at, this is like 10 to the negative 24th kilograms, right? You're trying to find the mass of something that is basically infinitesimally small, but yet we know it to a very, very high degree of precision. It isn't like we could take a proton, set it on the scale and go, oh, here it is, this is the mass. This is like, there's like a 0 and 23, a decimal point, and then 23 zeros to get to this. You all think it's cool when we use scales in the lab that measure out to 4 decimal places? This is like 0, 23, or decimal point, 23 zeros, and then this number, and then we know with a high degree of precision. So, here's the mass, 1.0073. This is 1.00. What is the mass of the nucleus of the most common isotope of carbon? Okay? Now, remember, look at carbon. All right, hey, the relative atomic mass of carbon is 12, right? So that means it's going to have 6 protons and it's going to have 6 neutrons. That's how you know the most abundant isotope of carbon is 12. If the relative atomic mass of carbon had been 13, you would probably conclude that the most common isotope had 7 neutrons and 6 protons. But since it's 12, you have 6 protons and you have 6 neutrons. Keep that in mind on number 10. When you get to this question, this is kind of like that multiple choice question. Here's your percentages. There's your atomic mass. Multiply the percentages by each atomic mass. Get the total average. This answer should be around, obviously around 108. That was a horrible version of that. 108. Okay. When you get to number 4, this number 4, percentage of aluminum that is aluminum, remember that's based upon mass. You need to find the total mass of the aluminum oxide, 2 times the aluminum plus 3 times your oxygens, and then divide that by the total mass of that aluminum based upon its relative atomic mass. When you get to number 5, this is formula units. Remember, if it's formula units, that just means that it's an ionic compound. If it's a molecular compound, we would be talking about molecules. Use Avogadro's number, 6.02 times 10 to the 23rd. Okay? On that one. On number 6, and I realize I'm kind of rushing through this, but hopefully this should kind of be a review anyway. So, you're trying to find the empirical formula on number 6. Remember, you're trying to find this ratio of carbon to hydrogen to oxygen. And you did this on one of the review problems. Remember, this is a ratio of atoms. It's also a ratio of moles. But it is not a ratio of mass. So you need to take all of these values, change them into moles, get the number of moles, and then divide that by the smallest divide everything by the smallest number of moles to get the empirical formula. Now remember, empirical formulas are the simplest whole number ratios. Y'all have done one like number 6 before. If you don't remember, go back and look at the review assignment. I've got it back to you if you don't remember how to do that. Okay. When you get to number, which one is it? Number 8. Okay? So, number 8 is a limiting reactant problem. And you know that it's a limiting reactant problem because you have hydrogen and oxygen. Now, clearly, when you get to number 8, here's the first thing you have to do. is you have to write and balance the chemical reaction. Because if you don't know what the reaction is, and if it isn't balanced, you're just dead in the water. So let's make sure everybody's cool. Anytime you produce hydrogen and oxygen react, you get water. Okay, that's it. So here's your reaction, hydrogen plus O2 yielding water. Balance the equation. I refuse to insult your intelligence by showing you how to balance this equation. For the love of all things, you can balance this equation. Now, this goes back to making the cheese sandwich analogy, okay? Figure out how much water you can produce from the hydrogen, how much you can produce from the oxygen. The smaller amount is how much water you can produce. The one that produces the smaller amount is your limiting reactant. So it's either the cheese, the ham, or the bread. Figure out which one of this produces the smaller amount. That's your limiting reactant. That determines how much water that you can produce. Okay, when you get to this last free response question, again, here's your percentages. Change those percentages into moles. Find that ratio. Okay, now what you'll see on this one, let me give you a hint. One of these is going to work when you take the number of moles and you divide by the smallest number. You should get 1.33 repeating 3. Well, that's the same as 4/3. So when you get this one, okay, one of these ratios is going to be 4/3. You can't have 1 1/3 atom. You can't have a third of one. So then you're going to multiply all of these coefficients by 3 to clear out the fractions. So if all goes well on this last one, you're finding this ratio of carbon to hydrogen to oxygen, and one of those answers obviously has to be a 4. So one of those coefficients is going to be a 4. And if you're not sure which one, figure out which one has the highest number of moles. That's what's going to be, whichever one of these has the highest number of moles, that's going to be the one that has the coefficient of 4. And the other ones are going to be something else. Okay, so let me stop the camera. That gets me through that. Then I got to load up what's going to happen with the buffered assignment. So I'm going to stop for a second. Okay, so now get you ready for the big buffered assignment. So let me kind of go over some things that you might see, like maybe on a quiz or test coming up at some point. So let's say that I gave you 2 pH curves. One is here, starts here, the other one starts a little bit higher, and let's say that this point right here is 7.00. And I'll tell you, one of these is a 0.1 molar solution of hydrochloric acid, and the other one is a 0.1 molar solution of acetic acid. Okay? So you've got 0.1 molar solution of hydrochloric, 0.1 molar of your acetic acid. I'm going to ask you, just based upon this information, which curve is your hydrochloric acid and which curve is your acetic acid? Now, there's a couple of ways you can view this. And this is where you tie in together a whole bunch of different things. One, realize that, oh, this is a strong acid. It's going to completely ionize. So since this completely ionizes, this is going to have a higher concentration of your hydronium ions, which in this case is going to be like 0.1 because it completely ionizes. Oh, that has a higher concentration of hydronium ions. You take the negative log of that, oh, that's going to get you a lower pH. So right away, just based upon this information, I know that this has to be my hydrochloric acid curve because, and here's the inverse relationship. The higher the concentration is of your hydronium ions, the lower your pH is going to be. Now, here you have acetic acid. It's a weak acid. It doesn't ionize very much. Since it doesn't ionize very much, it's going to start with a lower concentration of your hydronium ions, so that's going to have the higher pH. So you can figure it out that way based upon where this graph starts. Now, this is your volume of sodium hydroxide that you're going to add. Now, here's the other key thing that you can tell the difference. With hydrochloric acid, when it's completely neutralized, okay, so this is my hydrochloric acid curve, that has a pH of 7. because there is no secondary reaction between this chloride ion and the water. So that equivalence point right here is going to be right at 7 because there's no secondary reaction. Now, with your acetic acid, notice that that equivalence point is higher. That has a higher equivalence point because you're starting a secondary reaction of that anion with the water to reform the acid and hydroxide ions, okay? So since this has a secondary reaction, that's going to be higher. Now, but if you looked at the volume of base to neutralize them, here's the deal. If you had equal volumes of these two acids, hydrochloric acid and acetic acid, the volume to neutralize them is the exact same. Because you're going to have the same number of hydronium ions to pull off here as the same number of hydronium ions to pull off this weak acid. So everybody has this perception, it's like, oh, it's going to take more base to neutralize a weak acid or more base to neutralize a strong acid. They're the same. As long as they're the same molarity, and you can use MAVA equals MVVB, which is cool, okay? You can do that, but this calculation would be the exact same. It doesn't make any difference if it's a strong acid or a weak acid. It's the exact same calculation as long as the molarities and volumes are the same. Now, let's say hypothetically, I gave you this problem. Said, how many moles of potassium fluoride should be added to a 200 milliliter solution of a 0.1 molar hydrofluoric acid to produce a pH of 3.50? Okay? So number one, you have to realize, we're making a buffered solution because we're going to have hydrofluoric acid and then we're going to add the anion that goes with it. Okay? Now, the easiest way to do this is to look at kind of the big picture. All right. Here's the Ka of acetic acid, 6.8 times 10 to the negative 4th. There's my Ka. So if I take the negative log of this to get my pKa value, I get 3.17. So that tells me I'm kind of in the ballpark. Okay, hey, here's something I can work with. I only want a pH of 3.5. My pKa value is 3.17. Hey, I can do some tweaking of this. So if you look at your Henderson-Hasselbeck, pH equals pKa plus the log of your anion concentration divided by the concentration of your acid. So you want a pH of 3.50. Your pKa is 3.17 plus the log of your anions over your acid. Now, think this through. You know the concentration of your acid. That's a 0.1 molar solution. Okay, you know this number. What you don't know is the concentration of your anions. But look what happens. Think this through. You want this to be 3.50. This is where you want to end up, is 3.50. So what this means is that this log portion over here has to be a positive number, so that when I add that to 3.17, I end up at 3.5. Now, if this had been like 3, then I would know this would have been a value less than 1. That would have made that log a negative value. So, when I get done, I know that this log portion here has to be a value greater than 1 so that it's a positive number, so it in effect gets added to 3.17. So right away, think through the process. Just don't get wrapped up in the numbers. So, I know this, I got this. Basically, I need to solve for that. So, here's your sequence. Subtract your 3.17, okay? Then that's going to get you 0.33 equal the log of your anion concentration divided by your HA. Now, we need to undo the log. Okay, so this is a base 10. Now, this isn't negative log. Okay, this isn't pH. This is not negative log. All you're going to do, and this is a base 10 log system, so you're going to take 10 and raise that to 0.33. And that's going to get you your anion concentration divided by your HA, which we know is 0.1. Okay, we know that's 0.1 because I told you, oh, it was a 0.1 molar solution of hydrofluoric acid. So now you take 10, punch that into your calculator, raise it to the 0.33, multiply by 0.1. You get an anion concentration of 0.214 molar. Now, that matches with what we said at the beginning. If I take 0.214 and divide that by 0.1, I get 2.14. I'm taking the log of a value bigger than 1. I'm going to add that to 3.17. That's going to boost that pH to 3.5. So you can do a self-check and look at that and go, ooh, does that make sense? Yes, it does. Okay. Now, that's my molarity. Now, I want moles. So look at this. I got 2.14 moles per 1 liter, because that's what the molarity means. I'm only making 0.2 liters of this stuff, okay, because I said it was a 0.2 liter solution. So that's 0.22 liters over X number of moles, cross multiply divide, however you want to do this. And you get, oddly enough, 0.0428 moles of potassium fluoride. Okay? So if you take 0.214 times 0.2, you get this. Now, here's the problem. That's how number of moles that you need, and that's cool. But scales don't measure in moles. So if you were to actually measure this out in grams, and you were to do a conversion, 1 mole of potassium fluoride, if you multiply that by the molar mass, which is 58.1, trust me on that one, you get 2.49 grams of potassium fluoride. So if I take 2.49 grams of potassium fluoride, and I add that to 200 milliliters of a 0.1 molar solution of hydrofluoric acid, I should end up with a pH of 3.50. Okay. Now, speaking of salts that affect pH, one of the things that you have to think through, and hopefully I've done this enough that you can kind of get an idea. So if you look at like sodium chloride, if I were to take sodium chloride and add that to water, your pH is not going to change because the sodium isn't going to give up a proton to form hydronium ions, and the chloride ion isn't going to bond with the water to form hydrofluoric acid and create hydroxides. So if your cation comes off of a strong acid, off of a strong base like sodium hydroxide, potassium hydroxide, something like that, doesn't have a proton to give up, this isn't going to change it. If your conjugate base here is the conjugate base off of a strong acid, it's not going to change anything either. Now, but however, and we've done this, if you look at like potassium carbonate though, if I take potassium carbonate and add that to water, that carbonate anion is going to react with water. You're going to reform carbonic acid and hydroxide ions. Okay, because this is the conjugate base off of a weak acid. It's going to react with water. You can make hydroxides, the pH is going to go up. So here's the deal. If the cation has an extra proton, okay, like for example, NH4. So, but if I take NH4 and add that to water, the water is going to act as the base. It's going to take in a proton, and this is going to be the reverse of that reaction that we did on Friday. And you're going to get ammonium and H3O plus. So, if your cation has an extra proton to give up, an extra hydrogen, that's going to make the pH go down because of the fact that you're creating hydronium ions. If the conjugate base is off of a weak acid, your pH is going to go up because you're reforming that acid and hydroxide ions. Okay, so let me kind of get you through some of these problems. If it pulls up. Okay, so I'm going to send this out. Come on. Oh. Maybe it's the cold weather. There we go. Okay, so this first one, calculate solution formed by combining 50 milliliters of 0.1 molar solution of acetic acid and sodium acetate. This should be old school buffered solution kind of thing, okay? No worries. This one, I got a buffered solution. I'm going to make 20 grams of acetic acid, 20 grams of sodium acetate. I'm going to mix this in 2 liters. This is going to be pretty dilute. This is going to be a 2-liter solution. It's quite a bit of water. Determine the pH of the buffered solution. So here's the first thing that you got to do, and trust me on this one. Take these grams of acetic acid, okay, HC2H3O2, sodium acetate, and convert and find the number of moles. Notice this has 3 significant digits. Notice this has 3 significant digits. So when you do this conversion to moles, I would write that out where you have 4 non-zero digits. Both of these are going to be less than 1 number of moles. So I'd have like 0. You want to keep a lot of digits here and then round when you get to the end. Now, on B, I emphasize the word net ionic. I want to write the net ionic equation for the reaction that occurs when sodium hydroxide is added to this solution. So I want to make sure everybody's cool with what I want on B. So your hydroxide ions are going to react with the acid, they're not going to react with the anions, to form water and anions. So this is what I'm looking for this net ionic equation right here. Now, what's the pH of the solution after 140 milliliters of 0.1 molar solution is added to the solution? Now, here's what you want to do, okay? You have to make a decision on your stoich, because this is grams in 200 milliliters of the solution. So what I would recommend is that you're already going to have the number of moles. So on your stoich chart, I would just work this in moles, because you've got 140 milliliters of 0.1 molar solution of sodium hydroxide. So you can take 0.14 times 0.1 to get the number of moles. Now, but if you're hardcore millimoles, fine. Leave this as 140 milliliters, multiply 140 times 0.1, which is going to get you 14. So you're going to have 14 millimoles of your hydroxide. But when you do this, okay, you got to find this molarity, but then multiply that by 2,000 milliliters to get the number of millimoles of your acetate or your acetic acid. So here's the decision that you have to make when you're going to do the stoich here. If you're going to roll this into millimoles, which is fine, take 140 times 0.1 and you're going to get 14. That's cool. But then up here, you've got to take the grams, change that into moles, divide that by 2,000 milliliters to get the molarity, and then multiply that, take the moles, divide it by 2 to get the molarity, and then multiply that by 2,000 to get the number of millimoles. I don't care, okay? I honestly do not care. Just pick one. Now, let me give you some ideas of what some answers should be. So, out of the goodness of my heart. So, on number 2, your answer to B should be around 4.5, and your answer to E should also be around 4.5, and your answer to A should be around 4.5. So all of your answers on number 2, A, B, and C, should be around 2.5. Around 4.5. That's an ish, but it's going to be something like this. When you get to number 3 is like that problem that I just worked at the beginning of this video. The only difference is that I use potassium bromide and, no, I use potassium fluoride and hydrofluoric acid. This is sodium hypobromite, and you're going to add that to hyperbromous acid. You want to form a solution with a pH of 9.15. Notice this pH starts up quite a bit higher. And we start off quite a bit higher with this pH because this Ka is really, really, really small. So when I find this pKa, I'm starting with a much bigger value, okay? So that's why this one, I want to make a pH of around 9.15 because of the fact that this has such a big negative log when you take that Ka value. Now, when you get to, and this answer on number 3, when you get done, should be around 0.2 moles, okay? Should be around 0.2 moles. Now, when you get to 5, 6, and 7, okay? So, here's what I want to point out. This is kind of the summary of everything that we have done, okay? So, hold on, I got a text from my brother. I'll be right back. Sorry about that. That's the disadvantage of having a brother who is in the cattle business in this type of weather, and you're trying to keep cattle alive and machines running and everything else. Okay, so back to our story. This is why I teach. This is why I don't farm and ranch for you. Okay, so you're going to hit like this trifecta. So let me kind of point out the difference between 5, 6, and 7. So here you got nitric acid and potassium hydroxide. Strong acid, strong base, right? The net ionic equation, because it's a strong acid, is just H plus OH yielding water. That's all you have to have. Now, I'm going to add this amount of potassium hydroxide, 50 milliliters, 95, 100, 105. So, again, I swear to you, you keep this organized, you keep this straight. So here's what I want to see. When you get to number 5, okay, here's your sheet of paper, right? So I want the answer to A, B, C, D. I want this stoic here to match with this. Then listen to me. I want a space, okay? Then I want B, and I want the work here that goes with this answer. So help me, and this is recorded. If you don't do this, and I've got to sort through random stuff over here to try and match up with this, at this point, I swear to you, listen to me, I quit grading at that point. Okay, I am not going to grade the rest of this assignment. Not going to do it. You listen to me. I want, here's A, here's the work. Leave a space. Here's B, here's the work. Here's C, here's the work. I've got to grade a whole bunch of these, and I am not going to sort through random numbers about what's going to happen. Now, you don't have to write the reaction every time, because it's going to be the same net ionic equation of H plus OH yielding water. You don't have to write that every time, but you can keep these organized in a column coming down like this. Work in moles, work in millimoles, I don't care. Now, when you get to number 6, I got 50 milliliters of hypochloric acid is titrated with potassium hydroxide. Write the net ionic equation. Oh, this is a weak acid. Okay? So, with this one, you're going to have, here's what's going to be different. You're going to start with H plus HOCl, HOCl, yielding the anion in water. So this is what I want for that net ionic equation, and here's going to be the difference. So on number 6, you're going to have HOCl reacting with water is going to form OCl minus and water. So you got the hydroxide reacting with the acid. forming the anion in the water. I write this as the molecular form because of the fact that it's a weak acid. Now, when you get to number 7, here's the difference between 6 and 7. Still 50 milliliters of 0.2 molar solution of hypochlorous acid. Now, this is a buffered solution because now I got 50 milliliters of the sodium hypochlorous that's in the beaker. So here's the difference. 5, strong acid, strong base. 6, weak acid, strong base. 7, weak acid, buffered solution, strong base. That's the trifecta. So you got to look at the difference between 5, 6, and 7. And again, I cannot emphasize this enough. And I will go back and I will play this as a recording if I quit grading your paper. On these, you keep everything separated. You do not blend them together. You keep everything separated. Okay. All right. So I'll send this out probably Monday morning. And anyway, so here we go, kids. We're done. I'm going to go back home where it's warm. Actually, it's going to be cold because I got to go help my brother feed cattle.